Good afternoon, ladies and gentlemen. My name is Jan Barowski. I'm a researcher at the Institute of Microwave Systems at Bochum University in Germany. And today I'm here on behalf of the European Microwave Association in our first event of the EuMA Webinar series. The series aims at bringing together the international microwave community on a regular basis, by presenting talks on current research activities, but also on tutorial and introductory talks. And today is our first event. With me here is Anna Palles from Maxwell Applied Technologies, and we are both honored to present to you today a talk by Joachim Oberhammer, who's with KTH Sweden in Stockholm. Dr. Oberhammer is one of the international leading scientists in the field of micro-machined silicon terahertz systems, and will present today to us. Dr. Oberhammer got his PhD from KTH Sweden in 2004. He then was a postdoctoral research fellow at Nanyang Technological University in Singapore and Kyoto University in Japan. Since 2005, he's leading radio frequency and microwave and terahertz micro-electromechanical systems at KTH, and is a professor at KTH since 2015. He's a guest researcher still at Nanyang, or was in 2007, a guest researcher at NASA JPL in 2014, a guest professor at the Chair of Excellence at Universidad Carlos III in Madrid. He is author and co-author of more than 100 reviewed research papers and holds several patents. In 2004, 2007, and 2008, he got an award by the Ericsson Research Foundation, granted by the Swedish Innovation Bridge, and a scholarship by the Japanese Society for Promotion of Science. The research work is received 6 Best Paper Awards, several fellowships, and Joachim is committee and TPC member of various IEEE and European conferences and programs. So Joachim, we are looking forward to your talk and would like to give you a very warm welcome here. And maybe to the audience after the talk, so it will be about 1 hour, there will be room for questions using the Q&A panel, and Joachim and we are happy to answer your questions then. Okay.
Yeah, thank you very much, Jan, for the introduction and for giving me opportunity to show our work here. So as I just learned, this is the first talk in this EuMA series, so it's kind of interesting experiment for all of us. And I hope all attendees will enjoy it. I'm going to share my screen now. Hope this works also. And let's see whether I can get in presentation mode. Yeah, should see my screen, correct? You see the presenter view also?
Yeah, looks good.
Presentation view, okay, good. So yeah, my name is Joachim Oberhammer. I'm professor in microwave and terahertz microsystems at KTH in Sweden. And this talk is about a new technology, or a recently new technology, I would say. It's about silicon-micromachining for terahertz systems. And the question, or our research vision, is that this would enable a large-scale exploitation of the terahertz frequency spectrum. So this is KTH. It's could be off today actually, because today it's very nice weather here, but very often it's cold here and a lot of snow. So it's not always as nice as the picture here shows. So we are up in Stockholm, northern part of Europe, and here's just a short overview of my group. So we are 16 people in my group, have around €1.5 million per year external funding, €1.5 million per year external funding. We have our own clean room at KTH, which is a very important resource, and we have quite professional and production grade equipment there. So it's very different than our usual research university clean room, which is one of the reasons for our success. And I have my own terahertz laboratory. So we have equipment up to 750 gigahertz, including VNA and extenders, and also a custom built antenna measurement chamber up to 750 gigahertz. And this is fully automated, and also the probe station is the 12th degree of freedom, fully automated system with which we can do a lot of different measurements. Yeah, terahertz you heard, and you heard the microsystems. So we are trying to combine these two things, doing microsystems or micro-machining for terahertz frequencies. The terahertz spectrum is depending on who you ask, we get different answers. I think IEEE defines it from like 300 gigahertz up to 3 terahertz. And engineers usually define it as from 100 gigahertz upwards to 1 terahertz or even higher. And there are several frequency bands which are of interest, and these are typically atmospheric windows, meaning where you have not a high absorption due to absorption lines, which mainly is from oxygen or from water. And so a very popular, I would say, atmospheric window is in the 140 gigahertz range, the D band. So 140 up to even 170 gigahertz. You have a reasonable flat performance, atmospheric performance. And then another one is in the 200 gigahertz range. And then you have more in the 340 gigahertz range and even 650 and 850. So very often you see research which uses these specific frequency ranges, and that's because you have reduced absorption, let's call it like that. Something which is characteristic for the terahertz frequencies is that the absorption depends much more on the humidity in the air than at lower frequencies. So even at terahertz frequencies, you might have very low absorption if you have very dry air, but if you have higher humidity, then your signals are much more attenuated at terahertz frequencies than they are at lower frequencies. So this is actually interesting characteristics, which means that yeah, it should work reasonably well in countries like Spain or in indoor environments, but where it's very, very humid, foggy, you have much more attenuation. So you have these typical characteristics. So yeah, what are the opportunities and challenges of terahertz frequencies in general? Well, the good things is you have huge bandwidths. You have tens of gigahertz, even 100 gigahertz, and you can create very large bandwidth devices because the relative bandwidth is usually limiting the performance of a device. So you can get terabit per second easily, and you can get very high resolution for sensing applications, like when we talk about the localization of objects, like typical radar applications. You can have very, very small antennas. I will show an example about it soon. And it still penetrates non-metallic materials. And this is important for a couple of applications. And yeah, another interesting feature is that applies to radar or to sensing, that you can classify objects from which your signal is reflected by their surface properties, because surface properties or surface geometries are typically in the same order of dimension as the wavelength is. So this allows you actually to new ways of classifying objects in sensing applications. Disadvantages, well, we have some very high free space power losses, which scale with frequency, unfortunately. So the range is limited depending on power, what you have, to tens or hundreds of meters, depending also on what kind of antenna gain, of course, you have. But in general, your free space power loss are drastically increasing. You have a high sensitivity to air humidity, which I already mentioned. And there's some technological problems, meaning that the technologies which are currently available still allow you only to have a relatively small transmit power. And also the receiving side has much more noise in its receiving path. Like the LNAs typically have a much higher noise figures than at much lower frequencies. And there are, of course, many other technological problems, like system integration and volume manufacturing techniques in this frequency range are missing, at least from a system point of view. There are several applications which are very, very promising for terahertz frequencies. And this is Earth observation, for instance. So we are also working on satellite-based radiometers for environmental sensing. Medical applications are interesting as well. Radio astronomy, of course, that's where everything originates. Material detection or material characterization, and which can also be done remotely, like here for detecting explosive materials. You have security applications, general material characterization of many scenarios which are not possible with alternative methods. And of course, you have radar applications and telecommunication applications as well. But this here at the bottom are the classical applications of terahertz frequencies. I'll show you one example. which is actually interesting about antenna sizes. So this here is a antenna at 1.3 gigahertz parabolic dish. It has a 40 dBi gain, so it's quite a high gain actually, and it has a 9-meter diameter. So this here is my thumb, and the question is, could we put this antenna or an antenna with this kind of gain on my thumb? Yes, we can do that, and we did it already at KDH. So this is antenna array, which is 1024 elements. It's at 360 gigahertz, and it has close to 40 dBi measured gain. So it's close to 40 dBi gain, and it really is only 20 times 20 millimeter in size. So it almost fits on a thumbnail. So just by the frequency scaling, you can drastically reduce antennas. And this is a very nice benefit of terahertz frequencies. And yeah, the antennas are one of the major problems actually in telecommunication infrastructure, because nobody likes these base station masts, which are destroying the skyline of cities and houses and so on. So this is, if you want to have more ubiquitously distributed telecommunication infrastructure, you have to reduce antenna size. And this is one of the reasons why higher frequencies are interesting, besides, of course, the higher data throughput. Yeah, this is 11,000 times smaller. Yeah, and then the second approach from us, so going to higher frequencies and using different technology, which is so-called micromachining. So what is micromachining? Essentially, micromachining is a fabrication technology which has been used for 70, 80 years already. So it's about 70 years, I should say. As it comes from semiconductor clean room manufacturing of microelectronics. And microelectronics has clearly revolutionized our information age. And what microelectronics is, you have silicon wafers, and on top of the silicon wafers, you are fabricating your microelectronic transistors and transistor circuits, and with very, very high densities. Like there's Samsung, for instance, has a memory chip which is 200 billion transistors on a single chip. So this is very, very high integration density. So people use the same fabrication techniques, but not for doing electronics on top of the surface, but for doing micromechanics inside, or in the I would say 2.5D dimensions, so in a shallow layer, or even using the whole wafer. So this is so-called micromechanics, or MEMS, micro-electromechanical systems. And these kind of devices are around since the 80s, but the real breakthrough happened just in the 90s, so just 25 years ago. And nowadays, these things are everywhere. So in your mobile phone, when you rotate the mobile phone, the screen rotation is measured by gyroscopes, or there's accelerometers, and these devices are very, very cheap. They are less than €1 per device. They are in every mobile phone, in every computer. They are even in hard disks. Individual hard disks used to have this. Toys have these sensors. Microphones, as shown here, it's also a big application. 40% of the world's mobile phone microphones are MEMS technology based. So these devices are manufactured in billions of devices per year at very, very low cost. And they have clearly revolutionized sensors and user interface. So this was a second main success story of this microelectronics fabrication technology. Now not for electronics or for the signals, but now for actually sensing and actuation. People have used this micromechanics around 20 years ago for doing so-called RF MEMS, mainly switches. So using this for radio frequency applications, they did nothing else than micro relays, very, very small relays, so micro switches, and they had actually very good properties in terms of isolation in the off state and insertion loss in the on state, which is still by now much better than any analog electronics switch could do. But they never really had a breakthrough, because competing microelectronics switches were simply also improving over time and simply good enough that you did not need this performance, except for some niche applications. And now the next stage of this, and that's what my group is working on, we are using this micromechanics to go to higher frequencies and to solve the technological bottleneck in the so-called terahertz gap. It's the gap from 100 gigahertz to 10 terahertz, where you can say it's in between electronics and photonics. And there's a lot of key technologies are missing there in actually doing systems, in particular when it comes to high performance and also volume manufacturability. So this is our vision here, which most likely will never happen, but we are working towards it. But I would say that it could be that these terahertz micro-machined terahertz systems, which is called like that, they might revolutionize the terahertz spectrum. At least I'm sure they will play a major role in the exploitation of the terahertz spectrum. Whether you can really say that they will be the key factor to ubiquitous terahertz systems is difficult to judge from the point of view nowadays, but they will clearly have a major role in it. And I will show you a bit more about that. So why would you use micromachining for terahertz frequencies? What is the main benefits? Well, one key thing is micromachining is based on photolithography. Photolithographical processes in microelectronics go down to 5 nanometers. So I have here a mobile phone, which is kind of a recent model, and it has a 5 nanometer gate length on its transistors. We don't work with nanometers. We work down to micrometers or just below 1 micrometer. But you can, in any case, do very, very small features, which you cannot do with competing fabrication techniques. So you can do very small and very accurate geometries for higher frequencies. The higher you go in frequencies, the shorter your wavelength gets, and the more accurate you need to get your technology. Another key factor, and this is a really important factor, is the surface roughness. So when you go to higher frequencies where the skin depth is getting very, very low, the key factor determining your losses in like a metallic waveguide is the surface roughness. It's not the metallization thickness, that's totally irrelevant. It actually is only the surface roughness. So if you can do surface roughness down to nanometer, you have a very big loss advantage. And that's a key thing. Like this is a scan from one of our waveguides, and we have on the 2 major phases, we have a 2 nanometer surface roughness after metallization. And this is also unparalleled by competing technologies. So this is a very important factor, and this is the key behind the very, very low losses we are showing in our devices. You can do very, very high aspect ratio geometries, and high aspect ratio means here that something which is in one dimension very, very small and the other dimension very, very big. Like we can do a narrow septum here. So this is a septum in a waveguide power splitter. And this septum can be as narrow as aspect ratio is 110 to 1, meaning the structure is 110 times taller than wide. And this is impossible to do by CNC milling, for instance. When it comes to horizontal features, it's even more extreme. So I write here 1000 to 1, and I will show you, I think, 2 examples in this talk, where we have a membrane which even is perforated with accurate the fabricated holes. And this membrane is 1000 times bigger in diameter than it is thick. So you can really do this kind of very high aspect ratio structure, and they give you very good performance from a microwave point of view. Alignment accuracy is important when you assemble different structures. And well, within the chip, we have, of course, we are better than 1 micrometer given by photolithography, and also between the chips, we are better than 2 micrometer with current state-of-the-art technology. And this is very important when you go to higher frequencies, where the wavelength gets below 1 millimeter. And another important factor is the manufacturability. And this is, I think, is a key factor actually when terahertz applications are leaving the lab and going to making more use in society. So this micro-machining fabrication technique has proven itself in multiple applications, both in microelectronics and in the sensing applications, to be able to manufacture billions of very low-cost devices per year. So in high volumes, you have very low cost. And another important factor is the high product uniformity. And what people mean with that is that if you manufacture 10 million devices, they all have the same performance. and you don't have to do rigid quality tests, and then perhaps you have to throw away 80% of them, as you very often have to do when you try to do CNC milling at Terahertz frequencies. So these are very important practical aspects, which might really be a large-scale breakthrough for Terahertz applications. Another factor is that you can integrate MEMS, so these micro-electromechanical systems actuators, which allow you to make geometrically reconfigurable circuits. And I will show you a couple of examples of that. This is a bit more exotic, so this will for sure not be the first high volume applications, but this is something which is very interesting, and I hope at some point it will also happen in larger volumes. This is a complex slide which I did last year actually for an IEEE workshop, and it is about comparing different fabrication techniques with each other with different criteria here. It compares CNC milling with the silicon-micromachining, which I'm trying to promote, and with 3D printing, which has been, I would say, it has been in fashion for a long time now, but it's already on the way down because the limits have been reached, or there's improvements are going much slower now than 10 years ago. And also compared to electroforming or SO8 micromachining, which is a plastic micromachining technique. And we see from comparing the different aspects is that the silicon micromachining has the overall best properties, you can say, but there's of course some negative aspects here as well. And one of the major negative aspects is that the tool cost is very high. So the environment which you need for manufacturing this kind of devices is very, very expensive. And that means there's a very big technology introduction threshold. So if you would like to move into this technology, you have to invest a lot of money and you need a lot of competence to actually get a grip on this technology in comparison to, for instance, 3D printing. Other negative aspects are that the development costs are pretty high actually. But then when you go to higher volume manufacturing, you would actually get in much lower costs. And for instance, a CNC milling in higher volumes or even medium-sized volumes has extremely high costs, which is difficult to overcome. And when you have higher volumes, then the micromachining would have a very, very clear cost benefit as well. But the initial development costs are very high. I don't go through all the details here. I think we will share the slides anyway in one of the other ways. So this is an interesting overview table, I think. Yeah, let's look a bit, go back to the micromachining. This is a conventional Terahertz system by a European company in Germany. And this is how it typically looks like. You have CNC milled blocks. They contain waveguides, passive, active components. And the actual waveguides are very, very small, like at 400, 600 gigahertz, where we are here. The actual waveguide size is something like 0.5 millimeter waveguide width. So even less than that, actually, at these frequencies. So the actual waveguides consume a very, very little volume of this whole metal pieces, but you need these big pieces just to manufacture them stable and to handle them and to assemble them. So Terahertz technology is nowadays it's very much mature in terms of performance, nothing to say about that. But when it comes to the manufacturing technique, it's kind of in the Stone Age because it's very bulky devices, very heavy, it's manual assembly. They're super expensive, like each block here might cost several thousands to 10,000 of euros. And the whole system here might cost 50 or 100,000 euro. And therefore, this has mainly been interesting for scientific instruments. And you cannot volume manufacture this. So if I would order 10 millions of these per year, there's no fabrication infrastructure which can do this because it's a sequential process, the CNC milling, and you can simply not scale this. So if you want to go to higher volumes, you need, and to lower cost devices and systems, you need different technology. And that's why micromachining is promising here. So we are trying to put everything on a single silicon chip. This chip might be something like 1 centimeter or 2 centimeter side length. You can create your waveguides in there, by deep etching of silicon, and then you do metallization afterwards. And you can integrate any kind of component. So we have the waveguides, you have filters, you have antenna interfaces, you have sensor interfaces, power combiners, matching units, whatever, and also active components. So this will be a complete terahertz system integrated on a single chip. And this chip can be very, very small. It's only limited in size by the actual component size, which you try to integrate. So basically, you can make a terahertz system inside the wafer substrate, on top of which you usually make microelectronics. And this is volume manufacturable, much cheaper in larger volumes, and it is also having much higher performance because of, well, lower surface roughness and shorter distances, simply because it's smaller. Some examples here, some early examples from the US. This is JPL. They did a radar transceiver with 8 pixels, so it was a radar transceiver array. And the core of every pixel was a stack of 7 different silicon-micromachined chips. And the main reason why they did this is for size reasons and also for uniformity, because you want to have similar performance for every pixel. That's very important in an array. And that could not be guaranteed with CNC milling. So that's why they use silicon micromachining. Here's another example now at much more extreme frequencies. So this was at 340 gigahertz. It's now 1 terahertz. It's a 1 terahertz transmit system by a US defense company. And here they used the micro-machined waveguides for power combining of power amplifiers at 1 terahertz. Other examples here are from JPL as well in the US. So this is making a correlated horn antenna by stacking silicon micromachine chips. This, of course, is not a low cost application, but it shows something interesting you can do with this technology. Here's a silicon lens antenna where you use the silicon itself as the electric body, forming the silicon lens antenna at 1.9 terahertz. So you can use the technology for much higher frequencies than just going beyond 100 gigahertz. So this is a true technology which is truly scalable in size and in frequency to very high frequencies. So now I'll show you a bit about what we have been doing on this topic at KTH. So basically the goal is the silicon micromachine system. We have been starting with waveguides, and we have created the world's lowest loss waveguides. I will show a bit more about that. With very low loss waveguides, you can make very low loss cavities, and thus you can do record-breaking filters with extremely high Q factors, like Q factors close to 1,000 at 700 gigahertz, or in the D band far beyond 1,000. We have been doing MEMS phase shifters and MEMS waveguide switches in these waveguides. I will show you some examples about that as well. We have done also some sensor interfaces, and basically you need to create all the components which you need for making an electrical system. You need to have that in your toolbox in order to make a complete system. So this is like micro-machined absorbers, because very often you have to put a matched load on a terminated port for a device to work properly, even if you have an asymmetric loading of a device or unbalanced loading. So meaning a non-matched loading, then you need to terminate certain ports with matched loads. So we have to create as well. We have power combiners and the couplers are very important components, also more complex circuits. So we have been doing basically all the components except for the active circuits. With the active circuits, we don't do at KTH. We usually collaborate there with external partners. And we have been integrating silicon germanium, indium phosphide, and also gallium arsenide devices into our platforms. Yeah, antennas should be mentioned as well. I will show you some examples of some, I would say, quite high performance and interesting antennas, which you can do by silicon micromachining. I will start with the waveguides. I'll show you the waveguides in 2 bands. This is the 220 to 330 gigahertz band. We have 0.02 to 0.07 dB losses per millimeter, and this is around a factor 50 to 100 better than you would have in a planar transmission line. So the key point is you make rectangular waveguides, which are known to have low losses and are able to handle high power. But the high power is not an issue, or not well, would be nice to have it as an issue at terahertz frequencies, but you don't have high powers. But the key point is they give you very low losses as compared to planar structures like microstrip lines or coplanar transmission lines. And in the D band here is an example where you have even lower losses, so 0.008 dB per millimeter. And this is the best performance of any waveguides in any technologies in these bands. How do we achieve that? There's one, I will not go into the details exactly, but one trick is this low surface roughness, which I mentioned, like a 2 nanometer surface roughness on the larger side of the waveguide. And we can utilize this low surface roughness on the two larger side of the waveguides, because we manufacture the waveguide in a different way than people usually do when they make waveguides. So usually they do E-plane splits, because E-plane splits, you don't care about the quality of your split when you manufacture the waveguide, as there are no currents crossing the split. But in micromachining, you can merge different, you can stack different layers without with a perfect metallic bond, essentially. So you don't care about so-called H-plane splits. So we have even done waveguides with multiple H-plane splits, and you don't notice them because you have a perfect bonding between the two metallic structures. And these H-plane splits allow you to utilize the low surface roughness structures on a larger circumference of the waveguide than in the classical E-plane split. And therefore we have the lower losses. Some examples here of waveguides. So this is a coupler, which was actually designed by the Swedish Defense Research Agency in our process, 220 to 300 gigahertz, and it's a 3 dB coupler. And it has only additional 0.2 dB loss. Power splitters we have done, and I mentioned already these absorbers. So we are putting absorbers in waveguides for terminating ports. These are some key components which you need in making your systems. This is a much more advanced component, which is a very nice one actually, which you can do in this micro machine technology. So this is a so-called orthogonal mode transducer that basically is a device where you have two conventional rectangular waveguide ports, in which you have the TE10 mode. So we have one port here, one port there. These are the, let's call them as the inputs. And you want to combine the two signals in a common square port. And in a square port, you have the two input signals in orthogonal polarization. So they are vertical to each other. And that means that you would like to have very low leakage from one polarization to the other. And you can use the same antenna structure, for instance, and the same signal bandwidth for now, for instance, transmitting twice of the data rate, because you have two orthogonal polarization. And if they don't leak into each other, they can carry independent information. It's not only interesting for telecommunication, in which this is actually widely used to boost the data rate, but it's also interesting for radio astronomy applications, and also for polarimetric radar, for instance, or any kind of polarimetric sensing applications. The problem is that for making this kind of device, you need very complex geometries. Like you see, there's a lot of small features, like there's a lot of matching features here. There's power dividers. There is a 5-way power combiner here in the center, actually, which is, there's a picture shown here also, that component. There's very complex small features there, and they need to be manufactured in a perfect symmetrical way. Otherwise, you get a poor isolation of the two polarizations. And therefore, so far, nobody could do this above 110 gigahertz. And we have done this in micromachining by tripling the frequency, because we have much higher fabrication accuracy. And the device is quite small. So the whole device is 5 × 5 × 1 millimeter. So it's a very small device. We do this by etching 9 silicon layers and then stacking it together to form a single chip. This is just a cross-section of how we fabricate it, but I will not go into the details. Just some performance here, perhaps. The insertion loss is always an important parameter for any component. So both channels are better than 0.6 dB insertion loss. That's quite low for this frequency. You see also we have full band. So the whole waveguide band, 220 to 330 gigahertz, is covered by this. So you have a 110 gigahertz bandwidth, whoever would need that. You have a reasonable return loss for the whole band, better than 60 dB. And this is the key figure down in the bottom here. So the polarization, the cross polarization between the two polarizations in the combined square port. And here the floor is somewhere from 70 to 50 dB, and there are just some spikes which go up to 35 to 36 dB, some isolated spikes. And this actually is very good performance as compared to other OMTs in this frequency range, which is typically around 20 or 25 dB. So in our case, the worst case is 35 dB, and the floor is even down below the 40 or 50 dB. So this is a very nice example that you can do extraordinary performance with this micro machining, which is just impossible with any other fabrication technique. Yeah, filters with an exclamation mark. I mean, whenever we can do low loss waveguides, we can do low loss cavities, and that means you could do very nice waveguide filters. I'll show you some examples. This was the first one which we published 2017 actually. It's a 270 gigahertz filter. It's kind of narrow band, 1.85% fractional bandwidth. It is not just a single resonance cavity, so it has it's a dual resonator cavity, but it's also a dual mode cavity. So that's why we have 4 poles in these filters, and we have also 2 transmission zeros designed here, as you see, which give you very, very steep slope. And we had very low insertion loss because of the high quality waveguide cavities we involved here. And the unloaded Q factor, which is the key factor when it comes to comparing a technology, is more than 700 in this frequency range. So this was a world record by that time, and still is. Another interesting feature is also the filter can very simply be embedded between 2 waveguide flanges because it's an axial port structure, meaning that the input port and the output port are axial, they're in one axis, and the cavity filter is just built in between that. So there's two circular cavities which are dual mode each, and there's a coupling structure in between them. So you can very simply insert this into your conventional waveguide based system, and it's just 1 or 1.5 millimeter thick. We have done similar filter then at higher frequencies, like we go now to 450 gigahertz. We reduced the bandwidth here even more, so this is now 1% fractional bandwidth filter, and this actually was the first 1% fractional bandwidth filter ever done above 300 gigahertz. So the first 1% fractional bandwidth filter at sub-millimeter wave frequencies, and so far nobody could do it because they just had high losses. So we have Q factors here in the order of close to 800, and this allows us to actually have this low narrow bandwidth. And it's a reasonably complex filter, so we have 4 poles here as well. We don't have transmission zeros here, but it's a 4-pole structure. We did 2 different embodiments, circular one and a square-shaped filter structure. I don't remember now which one is this measurement here. Even higher frequencies, we did a demonstrator more for scientific purpose than for applications. So now we are at 700 gigahertz. It was published last year at IMS. It's a similar concept, dual resonance cavities with dual modes, and also here for 4 poles. And we could also do 1% fractional bandwidth filters at this frequency. And you see that we have now a Q factor which is 950. That's even higher than the one at 450 gigahertz, where we had 790. And then you might wonder, well, how is this possible? Because the Q factor should go down with frequency, and which is correct. So this should be something in the order of perhaps 500, but not 950. So we are twice of what we would expect. Well, the reason is we are over mode in the cavities here. So we are also playing with a few design tricks to get a higher Q factor. So basically, The reason behind this good performance of filters is first the good technology, and secondary, it's also some smart designs, to which a colleague in my group, Dr. Alexander Glubokov, he's the brain behind these filters here. Here's a more practical example for lower frequencies, D-band communication links. We did this together with Ericsson in Sweden. This is a D-band filter, has 5% fractional bandwidth, and it covers this channel here, 141 to 148.5 gigahertz. This is for point-to-point communication links. And this filter here is an insertion loss of less than 0.5 dB, and unruly Q factor of the resonators in the order of 1,500, 1,600. So this is very excellent performance, which you would not even need for this frequency range. But the key point here is the product uniformity, as I mentioned in the beginning. So you can really manufacture of this 100,000, and they will all have the same performance. We use this filter in combination with another similar filter for making a diplexer. Diplexer is a structure where you have one common port and two outputs or inputs, however you see it, like one for TX for the transmit and one for the receive, and you combine them in a single antenna port. And you would like to have a very high adjacent channel isolation. So we have now this filter from the 141 to 148 gigahertz bands, and we combine it with the lower band here, 129 to 134. And we have still a relatively low insertion loss. Now, of course, including the diplexer structure, it's a bit higher insertion loss. But we have very high adjacent channel isolation of more than 60 dB, which was the requirement for this. So this could easily be fulfilled by micromachining. There is something wrong here. Sorry. I'm not sure why the presentation jumped to the last slide. This will be the next slide here to be shown. I apologize for this. So this is another technological game which we played. We wanted to have a filter structure in plane of the waveguide, so not by stacking vertically, but we have it in plane, but still having actual ports, meaning one waveguide port on the top, one at the bottom. The way how we solve this is by combining an E-plane band and an H-plane band on the input and on the output, and then we are now the waveguide in plane of the chip. And now you can create any kind of filters in this technology. And you don't have any space limitations. So this is a cross section. So you see we are stacking multiple wafers together here and to create this. And here's also a nice cross section of our SEM picture, which is colored afterwards. You have one waveguide port here, one waveguide port there. They are axial, and we have these double band transitions on each side, and then we are in plane. And with this, we have done this kind of filters here. So there is one example here, which is a 5-cavity resonator, 270 gigahertz. And there's another example here, which is also a 5-cavity resonator, which in addition has 2 transmission zeros. So you have these transmission zeros here beside the filter. And we have, as expected, excellent performance because, of course, we have these low loss waveguides. Yeah, I move now to MEMS reconfigurable devices. So that is basically when you utilize micro-electromechanical systems actuators to make mechanical reconfigurable geometries of your system, which typically gives you high performance. So that was already known from the RF MEMS age. So when people tried to do micro switches by micromachining, so that you can use for transmission lines. So you have a transmission lines, you want to create a mechanical switch there by a micro relay, and these relays had really good electrical properties, actually, much better than any semiconductor switch, which has nonlinearity issues, power handling issues, and so on. And now the question is, how can we do this in a waveguide? So how can we do a mechanical waveguide switch? The solution which we came up with is to have a waveguide. So this is a rectangular waveguide cross section here. I showed a cut of it. This is a rectangular waveguide. And we have a curtain of small elements here. The small elements here, which are much smaller than the wavelength. It's very important. And we can actually have these elements either in a blocking configuration. In the blocking configuration, these small elements, sorry, I have a bit of a cold today. In the blocking configuration, these small elements form a vertical curtain, and in that way they are short-circuiting the electrical field lines, and the electromagnetic wave in the TE10 mode cannot propagate. And when they are configured in a non-connected mode, then the wave can penetrate through it freely because each element is smaller than the wavelength. And we can do this by moving around half of the elements by having integrated MEMS micro actuators, which I will show you soon how that works. And in comparison to a conventional MEMS, to a conventional waveguide switch, which is based on a motor, a rotary motor, which is rotating a waveguide section. This is 100,000 times smaller, lighter, much faster, of course, and it has almost equal performance, and it's just 30 micrometer thick. So this is thinner than a hair, this structure, as compared to this thing here, which is 250 grams and several centimeters big in size. We have done different generation of the switch, like here you see one at 700 gigahertz, where you have the waveguide cross-section and these small elements here, and here on the sides you have the actuators, where we can move around the different elements in the open or in the closed position. And we have done this for different bands, like first in the V band, 70 gigahertz, then 700 gigahertz. And nowadays we are working very application oriented, like this here is for space application, for radiometer in space. And we also use this for radar applications in the 300 gigahertz band, for instance. And like for this implementation here, we have for insertion loss in the order of 0.2, 0.6 dB, but isolation in the order of 35 to 40 dB. So it's actually pretty good on-off ratio of these switches. Another example of a mechanical reconfigurable component is a phase shifter, which is a very interesting principle. So we have a waveguide here, which is in this direction. And in this waveguide, we have two slabs or two bars, which are elongated dielectric blocks. So these are very long dielectric blocks. They have some tapered geometry on each side. And we can move these blocks laterally by having these MEMS micro actuators. So we can move one to the left, here, and the other one to the right, or we move them together. And because in a TE10 mode, there's an inhomogeneous, from a lateral point of view, inhomogeneous distribution of the electrical field. And when you have the electric bodies in this distribution and you move them laterally, you will change the effective wave propagation speed. And this actually results in a tuning of the time which the wave takes through the structure. So essentially it's a tunable true time delay. You see here nice in this top down SEM picture, the waveguide. So the waveguide is in this direction, and we have these two dielectric bodies, and we have the actuators on each side to move them around. There's some other features here, which I will not go into details how it works. The key point here is also the performance. So this is we did it at 220 to 330 gigahertz, and we had an insertion loss of 2.5 dB over the whole band for actually any kind of phase states. So quite low insertion loss. Sorry. And reasonably good return loss, like better than 10 dB for any state all over the whole band. Very linear phase shift. And the phase error for any state and any frequency is better than 4 degrees. And in the center of the band, we have more than, well, we have 440 degrees phase shift, which is more than the 360, which we would need for typical applications. And that's the phase shift has by far enough range to cover like beam steering applications. As compared to any previous work in this frequency range, we are by a factor of 3 or 3.5 times better in figure of merit, which typically is the degree in phase shift per decibel of loss. And that's simply because of this mechanical concept is so pure and has so low losses. let's discuss a bit about antennas. That's also a very interesting topic. Here's an early example which we did, even of a beam steering antenna. So this is a bit, I think I will explain it how it works on this diagram here on the right side. So you have an input port, and then the waveguide is actually spreading out into a parallel plate configuration. So if you have a parallel plate configuration, then the wave would spread out. And in front of that, we have a circular reflector, which was designed by the University of Rennes in France. And the circular reflector will reflect the wave back, and the wave will then travel backwards with a parallel wavefront, with a parallel linear wavefront, because we have this curved reflector. In addition to that, we are actually having perforations here, and then the wave goes to a lower level and travels back on a different level. I always compare this to how you build a house. You have a ground floor and a first floor, for instance, and in between you have an elevator. And the wave here is coming in, takes the elevator to the lower floor, and then travels back with a parallel wavefront. And then here we have a distributed leaky wave antenna, which will then shape the beam narrow in the other dimension, meaning in this dimension here. So the first curved reflector takes care that the beam is narrow in this dimension, and the length of the leaky wave antenna takes care that the beam is narrow in this longitudinal direction. The additional feature which you have here is that the beam direction, the outgoing beam direction, is frequency dependent, because the direction of radiation of a leaky wave antenna is frequency dependent. So you can use this for a beam steering in one plane. It's a very neat, very compact concept, and this was done at 220 to 300 gigahertz here as well. There's a lot of small other features there, but I don't have the time to go into all the details. Some performance here. Here's the diagram where we have the frequency and the elevation, and you see that the main lobe is changing its direction with the elevation. You see it also here in this diagram where we have the elevation and we have the beam pattern here. And the structure is like 20 times 20 millimeter. The whole chip is 24 times 24. We have a 55-degree field of view, around 28 dBi gain, depending on the angle, and also half power beam width down to 7 degrees. And we have done shown a first primitive radar demonstrator with this one. Yeah, that's shown here. Another example here, this is a corporate FET antenna array, which I showed in the very, very beginning. You remember this was the thing which was on my thumbnail. So we have done a 1024 antenna array, which is fed from a single waveguide board. So this is not beam steerable, it's a fixed direction. And the key problem here is that you have to make a distribution network from one input port to 1024 antennas. You want to have the same phase front, and you want to have low losses, because typically you have very long waveguides here that you distribute signals from the input port to all the antennas. And in a lossy technology, you would not get much power out of the antennas, depending on how big the array is. So here you see the cross-section. It's a 4-wafer structure, which I think in total we had something like 8 or 10 layers, which we etched. And it's super compact. So this is roughly 1 millimeter thick, or 1.2 millimeter thick. You see here the different geometries in the different layers. So you can really do these very small features very accurately in micro machining, and you can assemble that very accurately as well. So here's a performance. I just showed you one at the bottom here. This is the 1024 antenna element. We are in the 300 to 400 gigahertz band now. We have an 80 gigahertz bandwidth. I think I have return loss. No, I don't have a return loss anywhere here. But we have roughly 15 dB return loss for the whole band. Directivity is close to 40 dBi. The gain is 38.2 dBi measured gain. So this includes the array losses, the radiation losses, and the return loss. So we have less than 1.6 dB loss, this frequency, which gives a very high radiation efficiency. The lower size antenna, 16 times 16, 256 elements, so it's 4 times smaller in size, has even lower loss, so 0.8 dB loss, and more than 82% radiation efficiency. Here's just some pictures from the beam shapes. So here at 400 gigahertz, we have a 1.7 degree measured beam width, and of course you have some grating lobes here on the sides. I skip this slide here. Yeah, we have also been trying to put things together, making systems, and I'll show you some examples. So this was an early example of a telecommunication project. It's a D-band communication link. You might recognize this filter here. This was the diplexer filter, where we have one TX, one RX channel, and we have the common antenna port, and we have the filters in between for making a diplexer. And we put this on a silicon platform, and the silicon platform contains now much more. It contains the active circuits, heat silicon germanium chips, designed by Chalmers and manufactured by Infineon. It also contains the biasing network. It contains the bond bias. It contains the bypass capacitors. So everything on the whole RF front end on a single silicon-micromachined platform. There's a picture down here and a zoom up view here on the silicon germanium MMIC interfacing this micro-machined waveguide here. This was a project called M3 Terra, yeah, which finished in 2019. It's another example of a still ongoing project. It's a 238 to 248 gigahertz car radar. It contains an antenna array and power distribution network to the array, including also antenna tapering. So we do an amplitude tapering here. It contains in total 6 MEMS switches, MEMS waveguide switches, and some power combiners and some delay lines, because we are using this chip here for beam steering in one plane and also for beam shape switching. So we can switch between a conventional broad beam, which is used in a radar context, and also a notched beam, a beam which has a zero in the transmission in the center, and this notch can also be moved angularly. We can scan this notch, and these together, these two beam shapes together, give you actually complementary information about the scenery, and that has some advantages. So with this, we actually also moved into signal processing, because now when you make these radars with different beam shapes, you have to also to write the algorithms for that, for combining the data from the two signal shapes and figuring out the advantage. And we just submitted a paper now where we compare this combined conventional broad beam with a narrow with the notch beam of a two controllable antenna array, with more conventional beams steering of a 3 antenna or a 4 antenna interface. And the interesting thing is that our concept with only 2 antennas, but the beam shape switching, allows you to reconstruct the scenery much more accurate than the more complex or the bigger antenna arrays with 3 or 4 antenna elements when you do a frequency sweeping. It's kind of interesting. So the basic idea is that you would like to utilize a much reduced antenna array, reduced in complexity and in size, but you use different beam shapes, and which gives you complementary information. And in that way, you try to squeeze out more information, which would then be equal or better, like shown here, as compared to a large antenna array. So this is a way to reduce antenna aperture, chip size, and reduce cost, essentially. Yeah, this just some point-based functions, but for those of you who don't work with radar, they will not tell you much, so I will just skip them. But we benchmark different algorithms for our beam shapes. Yeah, we have also been working a bit on the electric waveguides, but not so much. But this is an interesting topic because a lot of people are working nowadays on substrate integrated waveguides. And that's why we try to do this also with silicon micromachining. So basically, the idea here is that you are using a silicon filled metal waveguide or a pure dielectric waveguide in silicon, which has some interesting properties. like here's an antenna array with the electric rod antenna array, where you have a tapered rods, and you can use this for beam steering when you can control the input. I will not go into detail how this works, but as photoconductive antennas there, you have laser beams shining on them, and you intermodulate them on this nonlinear element. So you do the phase shifting in the photonic domain, but then the beam steering is done in the microwave domain. And this kind of electric waveguides here is the advantage that it has much larger bandwidth than with conventional rectangular waveguide or metallized waveguide based elements. Here's an example of a substrate integrated waveguide in silicon. So we have basically a silicon core waveguide, which is metallized, and we measure this performance. Is worse than when you have a hollow waveguide, and that has to do with metallization issues and also with electric losses in the waveguide. But it's very interesting because it downscales the whole waveguide system by a factor of 9 due to the permittivity of the waveguide, and it it scales down the whole system. That's the main advantage of this action. Yeah, that brings me to the conclusions, and I actually kept the time pretty well, so Jan should not complain. I would like to say a few final words. So we believe micromachining is a key enabling technology for high performance miniaturized millimeter and sub-millimeter wave systems. The main advantages are that you have very small and accurate features, which allows you to go to very high frequencies, and you have this ultra low surface roughness, which gives you very low losses. So that gives you the high performance essentially. From a manufacturing and application point of view, you have very high product uniformity, meaning that you make 100,000, they all behave the same, and it's volume manufacturable, meaning you could make billions of them every year, and you already have the infrastructure in place for that. Yeah, these integrated micromechanics, like I showed you, we had integrated micro actuators for making switches and phase shifters. That is much more complex, but it allows you to do very interesting reconfigurable circuits, as I showed you. Yeah, I think at KTH we have shown many very high performance devices, which I showed you today also. Well, again, you need the whole toolbox of electromagnetic components to make a complete system. And yeah, we believe that in Europe we are not we're one of the leading partners in this micromachining, in combining this 3D micromachining and millimeter and sub-millimeter wave applications. This is a very expensive technology, so I will not go through the acknowledgements here, but you need a lot of big European projects and national projects to fund this kind of activities. But it's very interesting, and I can tell you my PhD students have a lot of fun with it. Okay, thank you very much for listening, and I think we have time for questions. I give the word back to Jan.
Yeah, thank you, Joachim. It was really interesting and very impressive to see. Yeah, to the audience, please feel free to write down some questions, and I think I will briefly read them and forward them to Joachim, but you can also see yourself then. I think there is already a question, and maybe while we are discussing that, several others will appear. Otherwise, I also have some myself. So one asked, how is the design workflow, for example, the simulation and verification, and how does it differ in silicon micromachining and conventional fabrication? Are there any special concerns that are to be taken into account? I guess yes.
Yes, that's a very good question, and yes, of course, has to be taken into account. But the design flow itself is pretty similar. What you do is you have to know your fabrication limitations and what you can expect from fabrication, and then you do your design. So very often our solutions look a bit different than what you would do in other technologies, because we understand both the micromachining world and the microwave world. So we try to get the best out of it by combining these two knowledges. So the knowledge in these two domains. But basically you make your microwave design, and then you fabricate it. And then you will figure out that, yeah, there's some fabrication imperfections, which, I mean, I mentioned you have micrometer accuracy, but you have, for instance, very often some sidewall under etching, some sidewall slopes. And these sidewall slopes, they're very well reproducible. So if you make it today and you make it after half a year in the same process, it will be exactly the same by micrometer accuracy, but you will have these slopes there. And you can, of course, tune them also with your recipes. Your etching recipes, we are using plasma etching for this. But basically, you have to live with this. But what you do then is that you take these slopes into account in your design. So when we design a very sensitive structure, like filters are very sensitive, or we are doing a very weird project right now with the European Space Agency, which is super complex in design. It took us more than a year to design this. And there you really accurately have to model what you would expect from fabrication, because these structures are very sensitive to very small deviations. So you basically have to know very well what you get from fabrication. You can do this by a test fabrication run or by experience with previous structures. And these fabrication issues, like this sidewall slope, unfortunately, it's not the same for all structures. It depends on the size of your geometry. It depends on the arrangement of your geometries. So there's a lot of knowledge actually in this. And there's also fabrication techniques which make your design very robust towards these fabrication issues. And we are employing these techniques sometimes. And we published, I think, 2 or 3 papers just on the topic alone, how to make things robust for fabrication. So this is actually a very interesting topic. So yes, this is very different. So, but it's the same also when you talk to there's people who do CNC milling at very advanced frequencies, and they also have to compensate. I mean, they know that the milling drill is not going in the shape as you draw it, but it's going more like this, and they have to predict the movement of the drill, and they have to predict the wear of the drill head to actually do accurate structures. So basically, whenever you try to go to the limit of a fabrication technique, you have to understand it very well, and you have to design your devices that they actually are suitable and that you can really squeeze out the maximum. But for very often you don't need this. Like if you make a simple waveguide structure or an antenna, antennas are very robust. You don't need to know this. But if you do filters or more complex microwave circuits, like we do in this European Space Agency project, then you really have to know very well your technology and the microwave design, and then try to. Very often we spend a lot of time in figuring out what is the best microwave design actually, and that we can really implement what we are doing. And with this, we get these results like this OMT, what I was showing, this automotive transducer, which is a very unique structure.
Maybe a brief follow-up question from my side, because you addressed it. In your answer, you explained that when you're at the limits of a technology, you have to take the process into account itself. Would you state that you are at the limits of this technology yet? Because when I look at the microscopy images, everything seems very perfectly from the design result. So the all edges are perfectly rectangular and all bends are fine. Where do you see the frequency limit of this technology?
Well, that depends on what you want to do. So, I mean, you can do waveguides at several terahertz, and I think JPL has done that also. They've done it like 1.9 terahertz. They have done waveguides, because for waveguides, the actual cross-section is not so critical. And that you see also, if you buy a cheap CNC milled waveguides, they work very nicely, even 300 or 500 gigahertz. And if you measure them, you see they are terrible out of tolerance. So it really depends on your structure. But if you want to do filters, like narrowband filters, you need to make very accurate irises between the cavities, for instance, or very accurate coupling structures. And there it's a bit more critical. So it really depends on that. The other nice factor is, though, that the higher you go in frequency, the less deep you have to etch. And the less deep you have to etch, because the waveguide is less tall, the less deep you have to etch, the more accurate is your fabrication. So that's why I really hate projects which are just around 100 gigahertz. And I have one of them where we are below 100 gigahertz, and I have another one where we are at 160 gigahertz. And I don't like this so much, because it's actually more difficult for us than to do things at 500 gigahertz or 600 gigahertz. Because simply the deeper you etch, the more difficult it gets, and you have to stack multiple devices. So from that point of view, yeah, I would say the frequency range we like is 300, 500 gigahertz or 200 to 500. But the main reason for that is the measurement, because the measurement technology gets also increasingly more difficult. Because for every device, you have to make some measurement interfaces. You have to match it with waveguide flanges. So that is actually a very big problem, the measurement technology. But from a prefabrication point of view, I think you can do things easily at 1 terahertz or beyond 1 terahertz. And if it's just waveguides, you can do it at several terahertz. There's no problem.
Okay, really interesting. Okay, so there's another question. I don't want to ask only my own. What kind of surface roughnesses do you achieve with this process? How are the different fabricated plates are joined together? So in fact, these are two, I guess.
Yeah, the surface roughness, I think I mentioned this top and bottom surface, we have 2 nanometers, and that's after metallization. Before metallization, it's actually sub nanometer surface roughness, because these are polished wafers. So they are one single crystalline plane in silicon. But after metallization, we typically have 2 nanometers. On the sidewalls, we have more, like we even kind of 100 nanometer. Now we just bought a new machine, which will be installed will be delivered in October, and that machine will give us a sidewall roughness of 10 nanometer, and that is very, very good. But these machines are very expensive, and that's the interesting thing. Actually, we are not using research tools; we are using production tools. So because production tools nowadays are much better than research tools when it comes to manufacturing. Unfortunately, the price is much higher. So if you want to buy this tool as a research tool, deep silicon etcher costs something like perhaps 400,000 euro, and the tool which we are buying costs 2 million euro. So unfortunately, these tools are much more expensive if you get to higher performance, but they are production tools, not research tools. Yeah, so that was the surface roughness, and the second part was how are we joining the different plates together, and we are using simple thermocompression bonding. So this is a process which has been known in micromachining for ages, essentially. There's nothing special with it. We have some special techniques for the alignment, especially when we work on chip level. But essentially, there's nothing special with it, and you can do this on bonding on chip level or on wafer level, for which you can use even standard tools like a standard wafer bonder. So there's nothing special on the joining, and it's very easy to join these wafers or these chips because they have this very low surface roughness and very low surface non-uniformity. So you just press it together essentially, and you apply a temperature around 200 degrees, and they will never separate. They're like one single block. So this is very simple.
Okay, cool, impressive. Then there's a question in the chat window. How about the power handling capabilities and of the different components? Is there a maximum power that you can feed through these waveguides? Well,
the power has to do with the losses, correct? The power handling of a structure has to do with how much heat you can remove from the structure. That applies to any microwave or any electronic device. So it has to do how much heat you generate and how much heat you can remove. And of course, the key point is the less heat you generate, so the less the power is dissipated, the less heat you have to remove, correct? And from that point of view, of course, if you have the world's lowest loss waveguide technology, you have also the best power handling technology. And another thing is that silicon has a very good thermal conductivity. And since all our waveguides are done in silicon, inside silicon, you can very effectively remove the heat. And of course, our rectangular waveguide has a very good heat dissipation properties because the heat is distributed all over the circumference of the waveguide and not just on the edges of a planar transmission line like in a coplanar waveguide. Heat or power dissipation in general is not an issue because the terahertz frequencies, you are happy if you have milliwatt power. Typically, you have much less than milliwatt power. So it has never been an issue for us, nor for anyone else using a much lower performance technology, because you simply don't have enough power at these frequencies. So power handling is not an issue.
Okay. Yeah, so currently, I think there are no other questions. I do have one. Maybe there appears some other things during the time. I would like to know, would it make sense to realize oscillators in this technology? So you have shown us pretty good and pretty narrowband filters. If you had an amplifying element, would it be possible to realize an oscillator?
Yeah, actually, we've asked about that a couple of years ago, because of course you would like to use this kind of very sharp resonators as external cavities for an oscillator. And you don't care about the losses. Like for an oscillator, you don't care about the losses so much because you have the active component part, but you care about the sharpness of the cavity, correct? And that would of course be ideal. So that, yeah, we discussed it a couple of times, but it never happened to get a project on it. And actually just this year, we submitted another application where we also want to utilize these resonators for oscillators, and in this case actually for coupling oscillators, for making them frequency robust and for coupling multiple of them together in a way of like a power combining. So basically you are power combining the power of different free running oscillators in a cavity which has a very narrow frequency spectrum. And yeah, if we get the funding for this project, then we will do it.
Okay. Yeah, interesting. Yeah, I think there are currently no other questions, but I think people see your contact, and yeah, I could also establish contacts if it's wished. So I would like to use this opportunity to thank you again, Joachim, for this very, very interesting talk. Yeah, thank you to all the audiences, and yeah, hope to see you again in the next installment of this series then.
Yeah, thank you for inviting me, Jan, and thank you for hosting this. Bye-bye.
Bye-bye.